Forget the northern lights, you know. On the largest planet in our solar system, a light show happens on a scale we can barely imagine. Jupiter's auroras are so gigantic they could swallow Earth whole, and their brightness is hundreds, sometimes thousands of times more intense than ours. They never stop. It's a perpetual and furious light storm at the poles of a giant world. But what feeds this cosmic storm? Where does so much energy come from? The secret isn't just in the sun, like it is here on Earth. The answer is much stranger and more violent. It involves a deadly dance between the most powerful magnetic field in the solar system and one of its most hellish moons. Let's uncover together the secret behind Jupiter's explosive auroras. To get an idea of what happens on Jupiter, it's worth taking a look here in our backyard. Here on Earth, the northern and southern lights are one of nature's most beautiful spectacles, and they're born from a direct relationship with our star, the sun. The sun doesn't just send us light and heat, it blows a constant stream of charged particles, which form the famous solar wind. This current travels through space at absurd speeds. Luckily, our planet has a protective shield, the magnetic field, or magnetosphere. When the solar wind hits this shield, most of the particles are deflected. But some end up trapped and are carried by the magnetic field lines to the north and south poles. When they arrive in our atmosphere, these energy-filled particles collide with oxygen and nitrogen atoms. Think of this as turning on a cosmic neon lamp. The collisions release energy in the form of light. Oxygen gives us the green and red tones, and nitrogen glows in blue and purple. It's an elegant process, directly linked to the sun's activity. When a solar storm occurs, our auroras become stronger and appear in places where they're normally not seen. It's a cosmic ballet with an external motor. Remember this idea. On Earth, the main actor is the solar wind. On Jupiter, the story is quite different. Now let's change scale. And when it comes to Jupiter, changing scale is an understatement. First, the planet itself. Jupiter isn't just big, it's a force of nature. Its mass is more than twice that of all the other planets in the solar system combined. And all this size generates our first protagonist, the most monstrous magnetic field in the solar system. Measurements from NASA's Juno probe showed that Jupiter's magnetic field is up to 20,000 times stronger than Earth's. It's such a giant structure that, if we could see it in our sky, it would appear larger than the full moon. And this field isn't just strong, it's fast. Jupiter rotates in less than 10 hours, dragging this magnetosphere with it at a mind-boggling speed. Imagine a cosmic dynamo, spinning non-stop and generating incredible energy. This is our first Titan. But every dynamo needs fuel, and that's where the second character in this story enters. One of its more than 90 moons, a remarkable small one called Io. Io isn't just any moon. It's the place with the most volcanic activity in the entire solar system. With more than 400 active volcanoes, Io lives in eruption, spewing lava and gases tens of miles high. Every second, its volcanoes throw about a ton of material into space, mainly sulfur dioxide and oxygen. Since Io's gravity is low, much of this material escapes and is captured by Jupiter's orbit. In space, the intense radiation strips electrons from these atoms, transforming them into ions. They form what scientists call the Io plasma torus, a giant donut of charged particles that surrounds Jupiter. So, we have the two Titans on scene. On one side, the strongest and fastest magnetic field in the solar system. On the other, a moon that doesn't stop spewing tons of particles into space. The stage is set for the big revelation. And here's the great secret of Jupiter's auroras. Unlike Earth, the gas giant generates most of its own storm. The process is internal, a magnetic tug-of-war of epic proportions. Remember Jupiter's magnetic field spinning wildly? It sweeps up Io's plasma like a cosmic mop. The sulfur and oxygen particles, which are much heavier than those from the solar wind, are caught by this relentless force. What happens next is one of the most efficient acceleration processes in the solar system. The rotating magnetic field works like a natural particle accelerator, taking Io's ions and hurling them at absurd speeds. These particles are then channeled by the magnetic field lines and thrown directly at Jupiter's poles. When this bombardment of heavy and super-accelerated ions hits Jupiter's atmosphere, the result is an explosion of light. The energy released in each collision is much greater than that of solar wind particles on Earth. That's why Jupiter's auroras are permanent and thousands of times brighter. They don't depend mainly on the sun's mood. Although solar storms can intensify the phenomenon, the real engine is internal. A violent symbiosis between the planet and its volcanic moon. NASA's Juno mission was fundamental in confirming this. Flying closer to Jupiter than any other spacecraft, it measured the electric currents and particles flowing between Io and the planet, proving that this connection is the main energy source of the spectacle. It's a self-feeding aurora generation system, something we don't see anywhere else in our solar system. But the story gets even more complex. The violence of this interaction produces forms of light that our eyes don't see. Jupiter's auroras don't just shine in visible light, they're extremely powerful sources of ultraviolet light and, most impressively, X-rays. To produce X-rays, you need an absurd amount of energy. On Earth, auroras almost never do this. On Jupiter, it's routine. The planet's X-ray auroras pulse with clockwork regularity, sometimes every 27 minutes. At these peaks, they can release hundreds of gigawatts of energy, enough to power all of human civilization for an instant. For 40 years, the mechanism behind these X-ray pulses was a mystery. It took combining data from the Juno probe, orbiting Jupiter, with observations from the European Space Agency's XMM Newton X-ray Observatory, orbiting Earth, to solve the puzzle. Scientists discovered that Jupiter's magnetic field lines vibrate from time to time. These vibrations create plasma waves, which work like a cosmic surfboard. Io's heavy ions surf these waves, gaining a final and gigantic acceleration before diving into the planet's atmosphere, releasing their energy as X-ray bursts. Telescopes like Hubble and, more recently, James Webb have been crucial for studying these lights. The Webb, with its infrared vision, showed that the auroras are even more dynamic than thought, with regions that change intensity every second, challenging current models and showing that we still have much to learn. These monumental auroras aren't just for show. They have a profound impact on the planet itself. For decades, scientists had what they called Jupiter's energy crisis. The planet's upper atmosphere was much hotter than models predicted, and no one knew where so much heat was coming from. The auroras are the answer. The colossal energy dumped at the poles by these storms doesn't just stay there. It spreads and heats the planet's atmosphere on a global scale, influencing the climate and overall temperature. The light show is actually Jupiter's global heating system. Studying this extreme laboratory in our backyard gives us a window to the universe. Many of the exoplanets we've discovered are gas giants, some even larger and hotter than Jupiter. They probably have aurora systems and magnetic interactions even more extreme. By deciphering Jupiter's secrets, we learn to read the signals coming from these distant worlds, better understanding the physics that governs planets throughout the galaxy. So the great secret of Jupiter's auroras isn't just one thing, but a perfect combination of extreme factors. It's a giant planet with the strongest magnetic field in the solar system, spinning at an absurd speed, and a small volcanic moon that serves as an infinite fuel supply. This dance creates an internal aurora engine, which produces the most powerful and lasting light show we know. From lights that could swallow our planet to X-ray explosions that pulse with unimaginable energy, Jupiter shows us planetary physics in its most radical state. And even with the help of Juno and James Webb, each new image seems to reveal more complexity and new mysteries. The gas giant still has many secrets to tell. If you enjoyed this journey to the heart of Jupiter's storm, don't forget to subscribe to the channel and turn on notifications so you don't miss our next cosmic explorations. And tell us in the comments, what other solar system mystery would you like us to uncover? Thanks for watching and see you next time.